Hi, I am Shahnawaz. This is the 10th lecture on metric spaces. We'll begin this lecture with the following theorem. So let Xt be a metric space. Then first part, empty set and the whole set X, whole space X, they are the closed sets. Part second, arbitrary intersection of closed sets is closed in X. Arbitrary intersection of closed sets in X is closed in X. And finally, finite intersection of finite union of closed sets in X is closed in X. Proof of first. So we will use the result that if a set F is open in X, then its complement is closed in X. So we are going to use this result to prove these three parts of this theorem. So we know that the empty set and the whole set X are open sets in X, so their complement will be closed. So complement of X, which is complement of the empty set in X, which is X, and complement of X in X, which is the empty set, are closed in X. So this proof was trivial. Now to prove second, let us consider let F alpha, where alpha belongs to lambda, be a family, be an arbitrary family of closed sets in X. Let us note, let F be equal to union alpha in lambda F alpha. So we'll denote this union by F. We have to prove that this F is closed in X. So we are again going to use the previous result, which states that a set is closed if and only if its complement is open. Therefore F complement, which is equal to union alpha in lambda F alpha complement, and by De Morgan's law, this is intersection alpha in lambda actually we have to prove the arbitrary intersection of closed versus closed. So here this is intersection. We have to prove the arbitrary intersection of closed sets in X is closed in X. So F is the arbitrary intersection of these closed sets. So this is here, this is the intersection, and by De Morgan's law this is the union alpha in lambda F alpha complement. Now note that each F alpha is closed, so this F alpha is complement, this F alpha complement where alpha is in lambda, this is open in X. So this is the union, arbitrary union of open set, so this will be open. Therefore F complement, which is equal to this thing, is open set in X by previous result. This implies, so we have proved that F complement is open in X. This implies that the complement of this set over here is closed in X. This implies F, which is equal to F complement is closed in X. So this proves the part second. Now to prove part third, we'll consider a finite family. Let Fn, where this n runs from 1 to n. Sorry, let us notice Fi, and where this I is an integer between 1 and n inclusively. So let this be a finite set of closed sets. Now what we have to prove? We have to prove union of this finite collection is closed set. Let H equal to the union iron is from 1 to n Fi. We have to prove H is closed in X. Now to prove H is closed in X, we'll prove H complement is open in X. Now H complement will be equal to the union iron from 1 to n Fi complement, and this is equal to the intersection iron from 1 to n Fi complement. One can observe here each Fi is given to be closed in X, so Fi complement will be open in X. So this is the finite intersection of open set. So this intersection over here, this is open in X, is an open set in X, and hence H complement, and hence H which is equal to the H complement. Now this H complement is open, so its complement, which is equal to H, is closed in X. So this proves this theorem. Now we are going to introduce the notion of continuity in metric spaces. Continuity. we know that for a real valued function f with a domain say A, which is subset of R, a rough and rather inaccurate description of continuity at a point say A in A is a statement that fx is close to f of A when x is close to A. When x is close to A. So this is a rough description of continuity at a point A in A. The measure of this closeness of two numbers or distance between them is the absolute value of the difference of numbers. In terms of the standard metric, say D on the set of real numbers R, continuity involves a relationship between D of x A and D of f of x f of A. This observation makes it possible to extend the concept of continuity to functions with the domain and range in metric spaces. So let us define the continuity of a function in a metric space. Let us consider two metric spaces. Let x dx and y dy be metric spaces. Be two metric spaces. A function say f from x to y is said to be continuous say at A belongs to A, where this A is subset of x. If for each epsilon positive, there exists there is some positive real number, say delta, such that when distance between x and A is less than delta, now this distance is in x, so this is metric x over here. So this should imply that distance in y between fx and fa, this should be less than epsilon. Or in other words, we say dy of fx fa is less than epsilon whenever distance between x and A is less than delta. Note that this x this is true for all x in A. So if f is continuous at every point of A, then it is said to be continuous on A. If f is continuous at every point of A, at every point of not this A, this capital A, then it is said to be then it is said to be continuous at continuous on A. So we'll prove a theorem. Now this theorem will give us the definition of continuity, which involves the sequential approach. Let x dx and y dy, x dx and y dy be metric spaces. And say, and let A be a subset of X. A function f from A to Y is continuous at A belongs to A if and only if whenever a sequence xn and bigger or equal to 1 in A converges to A, then the sequence f of xn and bigger or equal to 1, this must converge to f of A. Let us proceed to prove this. First we suppose that f from A to Y is continuous at A belongs to A, and we'll prove that this sequence converges to f of A given that xn converges to A. First, suppose the function f from A to Y is continuous at A in A, and let and this xn where n is bigger or equal to 1 be a sequence in A, be a sequence in A that converges to A, be a sequence in A converging to A. And now we shall show that the sequence f of xn converges to f of A. We shall show that the sequence f of xn where n is bigger or equal to 1 converges to f of A. Let us choose some epsilon, a positive real number. Let epsilon positive be a real number. Now it is given that f is continuous at A, then by definition of continuity there must exist a positive real number, say delta, then by continuity of f at a, there exists a positive real number, there exists some delta positive such that x belongs to such that whenever distance between x and a is less than delta, this should imply distance y distance between f of x and f of a, this must be less than epsilon for all x in a. So this is the definition of continuity. Now since it is given that the sequence xn converges to x in a, since this implies that limit n goes to infinity xn, this is equal to a. Now by definition of limit of a sequence, there exists some n naught. Since this is true, there exists some natural number, say n naught, which depends on epsilon, such that distance between the terms of sequence and a becomes less than delta when n surpasses n naught, i.e. the x distance between x between the terms of xn and a, this becomes less than delta whenever n surpasses n naught. This implies that, or therefore if n is bigger or equal to n naught, this implies y distance between f of xn and f of a, this becomes less than epsilon. So if this is true for any epsilon positive, this implies that thus limit n goes to infinity f of xn, this is equal to f of a, because this is true for any epsilon positive. So by definition of limit in limit of a sequence in metric space, we conclude that limit of f of xn is f of a. So this proves one direction. Now to prove the other direction, we suppose that every sequence, xn converging xn in a converging to a has the property that limit n goes to infinity f of xn is f of a, has the property that limit n goes to infinity f of xn is equal to f of a. We had to prove that f is continuous at a. We shall show that f is continuous at A. We prove this by the contradiction. Suppose if possible, f is not continuous at A. Suppose if possible that f is not continuous at A. So by definition there must exist some epsilon positive for which no delta positive can satisfy the requirement that distance between x and A is less than delta implies distance between f of x and f of A is less than epsilon. So there must exist epsilon positive for which no delta positive, for which there exists for which no delta positive can satisfy the requirement that the x distance between x and A is less than delta implies the y distance between f of x A and f of A is less than epsilon. So for this delta, this condition does not hold, this requirement does not hold. So this means that for every delta positive this means that for every delta positive there exists some x belongs to A such that the x distance between, if it is given the if it satisfies that the x distance between x and A is less than delta, but the y distance between f of x and f of A is bigger or called epsilon. Now for n belongs to n, I mean n is a natural number, the number 1 over n is obviously a positive real number. And therefore there exists x n belongs to A such that the x distance between x n and A is less than 1 over n, but the y distance between f of x n and f of A is bigger or equal to epsilon. So the sequence x n then converges to A, but the sequence f of x n does not converge to A. This contradicts the assumption that every sequence x n in A converging to A has a property that the sequence f of x n converges to f of A. This implies the sequence x n converges to A, but the sequence f of x n does not converge to f of A. This contradicts the assumption that every sequence x n in A converging to A has the property that f of x n converges to f of A. Therefore, the assumption that f is not continuous at A must be false. Therefore, the supposition that f is not continuous at A must be false. So this completes the proof. Thank you so much.